So a basic outline of the talk is I already gave away the punchline that the Beam does not actually implement the actor model. So you can all leave now if you have better things to do. So we'll talk about the definition of the actor model and how it's argued about in the context of the Beam, and then try to give you a brief overview of Pony. I don't have nearly enough time to give a good overview for programmers. So hopefully I can give you just a little teaser. And then we'll start talking about the actor model, and if you're implementing an actor model language or framework or something like that, some of the design choices and implementation choices that you'd have to make, and then compare what the Beam does and compare it to the Pony language. So with that, we'll go along. I hope by the time you leave, you have a much better understanding of what the actor model is, and maybe even describe it well to someone else. And then the many different dimensions of design and implementation of how you might build an actor model system. Beam and the Pony are actually quite similar, except where they're not, and to realize where those differences are, I think is useful. Especially when comparing and contrasting with other frameworks, like Agha, for example, something else in industry. And then hopefully Pony is interesting enough that you might want to give it a try on your own computer. And it is the 17th of May. Happy Constitution Day to Norwegians throughout the world. So with that, again, there's a summary that there's actually a conversation on the Erlang Questions mailing list that I'll talk about in more detail that had a big argument about whether or not this statement was true. So if you look at the definition of the actor model from today, that you'd see that the actor is the fundamental unit of computation, and this is made to be intentionally broad and far-reaching, and I'll talk about that a little bit later. So an actor has its own state, whether it's registers, memory, heap, all that stuff, and that an actor can read and modify that state, but nobody else can. So in the Beam world, this should sound very familiar in that each Erlang process has its own private heap, and under the hood there are the registers happening inside of the Beam, but no one else, no other process has access to those, except for small little details like process info and other sort of debugging and maintenance stuff. So as it's defined in various papers throughout the years, the three major properties of an actor then, aside from this fundamental computation notion, is that you can react to a message that you receive, or you can create a new actor, and implicit in that is that when you create a new actor, you know the name. So it's like with Beam, if you use the spawn BIF, that you're told what the PID is, but then it's up to you to share that PID with someone else. And so then the third thing is message passing. You can send a message to another actor. And that message passing is the one and only communications mechanism between actors. So the actor model actually has a long history that goes back to 1973. Hewitt Bishop and Steger had published this paper. My glasses are terrible. Universal Modular Actor Formalism for Artificial Intelligence. I think all three of them were from MIT. I'm not 100% sure. This is a paper that if practitioners today read this paper and you get to the end, you're like, you know what the actor model is? And the answer is no. Like it's a vision statement. It's an ambitious vision for the future of what applications for AI would look like if they were written with the actor model as their foundation. You probably don't have an understanding of what an actor is, how it's defined, how you would build an implementation. But it does have lots of cool quotes from William of Ockham and Shakespeare, and a lot of Lewis Carroll. it makes for interesting reading. Irene Greif, I hope I'm pronouncing her name right, wrote a PhD thesis in 1975. That was the semantics of communicating parallel processes. She was the first woman to graduate with a PhD in computer science from MIT. This was her PhD thesis. Hewitt and all of the other collaborators cite her thesis as being necessary foundation for all of the work that they do subsequently. So she had a very large part in defining the model. The next paper in 1977 is probably the most cited paper about actors by Hewitt and Carl Hewitt and Henry Baker, Laws for Communicating Parallel Processes. Just to take a couple of sentences out of the introduction, it says, quote, in this paper, we argue that in a distributed computation, the notions of local state, local time, and local namespace should replace those of global state, global name, and global namespace. This replacement of local notions this replacement of global notions for local notions for global notions is equivalent to the reformulation of computation in relativistic terms. So if we fast forward to the beam today, that the process is a thing that has its own local state. It reacts to events that are delivered in your mailbox in some unknown global order, and you deal with them either in order, or if you decide to screw up the order and use selective receive, that's up to you. First book about actors was Gul Agha's PhD thesis from MIT, and I think he finished it in 85. The book is 1986. And here's where we find the three rules that I had mentioned earlier. He uses much different nomenclature than you would typically find in things today. So an actor is defined by 5 things in his case. The first 3 I already mentioned. A behavior definition, which associates a behavior schema with an identifier. So that means that it's a binding between a message, incoming message type, and a script or a program that runs in reaction to receiving that message. A new expression, which creates new actors. And then there's a send command to create tasks, which is the word that he uses for a tuple of a unique identifier and a recipient address for a message, and then the communication, which is the message data itself. And what's interesting is that Agha is now going beyond just the simple theory of earlier papers, but he is introducing sort of real-world complications in that actor systems need to communicate with the outside world. And we heard about this yesterday with the morning keynote with Peter Van Roy. Dealing with the outside world actually makes computation a little useful. So there's this notion of a receptionist, which is a list of actors that can receive messages coming in from the outside world. And then similarly, point number 5 is a list of actors that can communicate out, send out to the outside world. The authors were trying to be very intentional about saying that this actor model is a very general notion for computation, and the intent was to describe all possible computation in the same way that Turing machine or lambda calculus is universal. The bit here I've accepted from one of Carl Hewitt's papers from 2010 or 2015. It has like a 5-year publication range. He's updated this document like 30 some times. But here, point number 2 is really interesting. The following are not required by an actor: a thread, a mailbox, a message queue, its own operating system process, etc. So we're used to thinking that the notion of mailboxes and queuing is part of an actor model, and Hewitt and collaborators are aiming at a much more general notion. So Here's from the 1977 paper. This is describing a cell, which would be a single memory word or single memory location, and that it responds to two types of messages. There's the contents message and the store message. And when a cell receives a contents message, it just it sends the name of its acquaintance, which meaning the value of that memory location, and sends it back to the reply to address. And then when it receives a store request, it memorizes the new contents, making y the acquaintance in the terminology of this paper, meaning that it sets its private state to the value y. So we've just described memory in a von Neumann machine here, using the notion of actors. The names of actors are quite important in terms of locality. So Hewitt and Baker say that you need to know about the existence of another actor, and you need to know its name. And the only way you can send a message from actor A to message B is that if A knows about B. So A must know B's name. And the only way you can get that is if you created actor B, or you got B's name in a message earlier somehow. So again, in 2010, Hewitt reformulates these three rules that to get the name or an address or a PID, if you're in the Beam land, of some other actor, that you had to get it in a message. Someone had to tell you that B exists and what its name is, or you already had it in your own private state, or you created it yourself. So here's where Erlang screws things up. Using the BIF list to PID, we can invent PIDs out of thin air on the Beam, and this is in direct violation of the rules of locality here. We screw up these three rules by providing a fourth path. So this voids the warranty on the formal definition of the actor model. So this Erlang questions mailing list discussion that I had referred to earlier was a conversation about Go versus Erlang, pros and cons for distribution. And Miles Feldman had piped up and said that I see Erlang as an implementation of the actor model, a la Carl Hewitt. And Pierre Stritzinger, is Pierre in the room here? Or is he off at another talk? He said, this crops up again and again, and it still isn't true. So shots fired. And in the thread, which I highly recommend reading at erlang.org, you can find a link to the mailing list archives and go back to June of 2014. You can find this thread, and some of the arguments that were made is that selective receive reorders message delivery, message receipt by the receiving actor, and that violates the principles of the actor model. Process links and monitors both. This extra message sending as a result to actors and monitors firing is unactor-like, and Carl Hewitt in particular really hates the idea of actors being crashed by links that are broken. Someone had argued that preemptive scheduling, you could make an argument that the preemptive scheduling that happens inside of the Beam VM also is against the actor model. Hewitt himself, in that paper from 2010, he said that Erlang has some big problems, and one of them is that it doesn't use messaging exceptions, like messaging with a capital M. And nowhere else in his writing does he say that exceptions are sort of required, part of the model, which is a little odd. Dying is just very bad. Process death is bad. And then also, inactive actors aren't garbage collected. They have to explicitly die in order to be reclaimed, and he feels that's bad also. So in response, Robert Verding says, thank God we didn't know anything about the actor model. We would have gone down this rabbit hole of like, what is the actor model, and are we doing the right thing? Are we going to make Carl Hewitt happy if we ever see him at a conference or something. I'm filling in there. You can actually read it. He says we were actually trying to solve the problem, telecoms, switch development, maintenance, etc. And this was the best solution that we could come up with, and that it was purely pragmatic. And we took ideas from other inputs. And both Robert and Joe Armstrong were in on this thread and replying of where they got their inspiration from, like Smalltalk systems, for example, or Area Pascal was also mentioned, an earlier language from Ericsson. And it happened right when I had a diagram that I was going to show. So while we wait for the display to come back, I'll go to the next section for the talk outline and try to. Oh, we have a diagram again. Yes. Diagram. So, all right, what's Pony? So, Pony is a language with a lot of with a type system that is based on a type of typing called affine types, and affine types are also used by the Rust type system for keeping track of notion of ownership of pieces of data. Pony has more flavors of access control embedded in the typing, more variations than Rust does, but the notions of ownership are similar between the two if you know anything about Rust. The language is type safe. The compiler is very picky, very, 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 very picky in checking all of the types. It's also memory safe and exception safe. So once the compiler gets through its work, if it compiles, your program is automatically data race free, which is pretty amazing. All the messaging is done by pass by reference. So in the Beam, with exceptions, but the semantics are that data is copied from the sender's private state and copied into the mailbox, which is sooner or later ends up being part of the heap of the recipient process. And that copying, of course, has a penalty the bigger the data that you're being sending, again with the caveats of reference counted large binaries and other sort of optimizations in the Beam today. But has anyone heard of the Erlang project, which compiles Beam bytecode into Java classes and then runs them directly in the JVM? And in Erlang, sending messages is done also by pass by reference. And in certain micro benchmarks, it just blows the doors off of Beam because there is no expense of copying this data to the receiver. The type system is also then guaranteeing that all data that's shared between actors is safe. There are no data access races. So you don't have problems with adding locking code or synchronization to your application code. There are no deadlocks. There's no memory model ambiguity. No concurrency composition problems. And everything in the type system is done by the compiler, so there's no runtime overhead for the data typing once the program is running, which is quite awesome. The type system is aware of concurrency. It's aware of actors, and so it's aware of when you send a message and you send data in a message that, oh, I need to do some extra type checking to make certain that the access for this particular alias, is it readable, is it writable, can I compare identities, is that compatible with sharing this data to another actor? And if you have questions about that later, feel free to ask in Q&A. The Beam, as we all know, compiles down to Beam bytecode, and you have the option of using hype, and soon we'll have the option of using a JIT to get down to native CPU instructions. In the Pony world, we use the LLVM toolchain to compile down to bare metal, air quotes. The executable also has dwarf symbols included. So if you fire up a profiler or debugger that you can use from GNU project LLVM, or if you use the Intel-based toolchain, that it all looks like weird C++ to the debuggers, but it all works for debugging, inspecting, stopping and starting. Pony actors don't crash; they're type safe. And so there's a bit in the syntax that requires you, when you call a partial function, meaning that the function may raise an error, that you have to put a question mark by it as a visual reminder that you're doing something that is potentially exception worthy, and that you must catch that exception, or the compiler again will fail. And so if your actors objects are no longer crashing, then you reduce or eliminate, depending on your point of view, the need for using links and monitors for managing notifications for the death of actors, because they don't die until there's nothing left for them to do. There is one heap per actor in Pony, which is very similar to the Beam VM, and that each Beam process has its own private heap, and that heap is garbage collected on an individual basis. So there is no global synchronization required for garbage collection. There's no stop the world. The default in many JVMs, for example, so the GC is fully concurrent. There's no synchronization points or locks or barriers aside from those needed for the lock-free data structures in the C runtime that is linked in with your Pony application. The message passing is maintained in shared objects. There's I think it's a dual counter of local alias count and a remote alias count. So when you send a message, you can increment your remote counter, and when some other actor has its counters go down to 0, it actually uses the same internal infrastructure for sending messages. So there's what's called a system message that is sent to the original allocating actor's mailbox, and then your application code doesn't see that particular message, but it's pulled out of the mailbox in causal delivery order, and then that message says decrement the foreign reference count. And so this messaging is used for maintaining global information about whether an object is alive, despite the fact that you may have created it weeks ago and sent it off to who knows whatever other actors. So the garbage collector and the type system was co-designed. The name of this garbage collection protocol is called Orca, as in like killer whale. So you can look it up online. And one of the things is that these actors are first-class citizens, and so they're also garbage collected, and the runtime halts when all of the actors in the system are eligible for garbage collection. Then the runtime automatically shuts down. So all these really nifty properties of like speed, yay, and then all of the lovely goodness in the Erlang and Elixir land. And wouldn't it be great if we could mash them together and have an Erlang Pony? Like, that would be awesome. That would be really cool. But if we were to have such a thing, maybe let's look at some details of what would really be needed, what things are similar versus different between the two systems, and see how feasible such a thing might be. So we're going to be looking at 20, 25 different things, but they're in various groupings of properties of message sending, or of message receiving, or of actor or process scheduling. Message delivery guarantees for the academics who are doing implementing distributed system protocols. Need to know things like can messages be corrupted in transit or lost or reordered? I'll talk about that. And miscellaneous stuff like actor lifetime and Byzantine behavior, craziness like that. So we'll go through a lot of these. Is message sending synchronous? In both cases, the answer is no. That's asynchronous message passing in both Beamland and in Pony. Where do you send, or pardon me, I'm getting ahead of myself. Are processes named or not? And in both cases, yes. Actors have a name, and if actorish things. So in Beam, it's the PID. If we ignore the process registry, which you can model as yet another Erlang actor, that the name of a process is the PID. In Beam and with Pony, it's a tag address. And then what is the message destination? And in both cases, it's either one process or one actor, that there's no built-in multicast or broadcast or any cast. There's no notion of a channel, which you can send a message and some unknown to you actor or process receives. So there's the same there. Here's our first major difference. Our messages typed, and at compile time at least, in the Beam they're not typed. You can send any message to any process. You might get some weird results if you send an arbitrary message to a port in the VM, because ports are sort of magical processes, and they have a very limited vocabulary. Pony is the messages are very strongly typed, and the compiler is going to yell at you. So here's a major difference. Whoa, ponies go, whoa. People tell them to say whoa. Never mind. All right. So how does data appear in a mailbox? Again, here's a difference I talked about earlier, that with Beam, there's copying happening to the destination heap. There's a lot of optimizations and special cases in the implementation of the Beam, so that the data doesn't go directly into the destination heap, but it eventually gets there. Pony, they're reference counted. And if there are questions about how that works, if I went too fast or omitted some details, please let me know in the Q&A. Is message delivery reliable? And if we consider the single machine case, and if we ignore details in Erlang, for example, of if you send to a registered name and that the PID behind that registered name is dead, then you get different behavior. But if we ignore those details, both systems have reliable message delivery. And there's a side effect of this reliable message delivery that we'll talk about a little bit later, related to memory use. The message delivery order. What's the message delivery order? And in Beam, it's anything. You have selective receive. You can pull messages out of the mailbox in any arbitrary order that you wish. And with Pony, the receiver handles them in FIFO order. So the Pony runtime will guarantee that the order that the messages are put in the mailbox are delivered in causal order, and then the recipient deals them in first in, first out order. And the reason for the causal delivery is because of the garbage collection messages are also being sent with the same message passing mechanism, and you don't want to screw up the causal order to get the reference counts wrong if you did a selective receive and you grabbed a reference to something, and then later the garbage collector accounting messages arrived in a different order. Causal message order guarantee in the Beam, yes, if you do not use selective receive. Inside of a single VM, if process A sends messages to process B, messages, X, Y, and Z, then the order that they would be in the mailbox is also order X, Y, Z, and it's up to you to not use selective receive to preserve that order. Is message receiving, is it blocking or not? And of course, in the Beam, yes, you can block waiting for a particular message, again using selective receive. Pony, no, you don't have that choice. Again, it's FIFO only. For message receiving, are you aware of time? And in the Beam, yes, you can say you use an after clause in your code to say I'm willing to wait up to 0 milliseconds or some number of milliseconds, or an infinite amount of time when you don't care. In Pony, there is an awareness of time, but these messages are delivered by a separate timer subsystem, and so those messages are sort of independent of other messages. In the category of scheduling, so who's scheduling actors is a very similar sort of thing, where both the VM and the Pony runtime have scheduler processes. It's typically one per core. They're running inside of the context of a UNIX or Linux pthread, or in Windows, whatever the operating system thread equivalent is, and that there's a similar sort of work stealing that happens if one scheduler has a long run queue with many processes or actors waiting to run, and another scheduler is idle, then the one with idle or the empty queue will start stealing runnable processes from the other schedulers. What's the overhead for scheduling? The Beam and Pony, they're both pretty cheap in terms of a few hundreds of bytes to represent the basic data structures for both a process or an actor. It doesn't take long to create or destroy them, so let's call them cheap in both cases. And then also scheduling hundreds of thousands or millions of these things, as long as you've got the memory on the machine for it, that's also fine. A big difference here with scheduling, is it preemptive? And in the Beam, the answer is yes. In Pony, the answer is no. So as a Pony application developer, because you're using cooperative scheduling under the hood, you have to know where those potential scheduling change points can be in your code. So if you write what's called an actor message receiving function, that you can't have that thing run for days or hours or even long minutes without starving the scheduler, because you don't return control to the scheduler. So it's a similar sort of thing in Erlang. If you're writing a NIF, for example, and your C code inside of the NIF says sleep for 15 seconds, then you cheat the scheduler, the reduction count based scheduler inside of the VM. Are there priority schemes for scheduling? And Beam, of course, has the notion of the maximum, high, normal, and low priority schemes. Pony, you don't have that. Is there work stealing? I mentioned that. Yep, in both cases. Can schedulers go to sleep if there's no work to be done? That after a certain amount of time, you do work stealing and you find out there's no work to be done. In both cases, the schedulers will shut down and conserve energy. So that's awfully nice. Are there mailbox size limits? No, in both cases, and of course that comes with all the advantages and disadvantages of using potentially infinite amounts of memory for queuing things in your mailbox. But this also has a side effect that if you don't drop the messages due to memory limits, then you can say that you have guaranteed message delivery. And that gives you some other very nice properties for reasoning about the behavior of your program. Is there limits on the maximum heap size? No, in both cases. And so again, that comes with all the advantages and disadvantages of that design choice. We already talked about the expense of actors and processes. They're both pretty cheap. Can actors crash? In Pony, no, they don't. And of course, Erlang Beam processes certainly can and do. Is there scheduling back pressure? So if a recipient, if some process is being overloaded because it's being sent too many messages, that the overhead of processing the messages is more than the total incoming delivery rate, then of course you have potentially a unbounded mailbox size. Is there any mechanism to help prevent that problem? The Beam used to have such a thing, and it was removed like a year and a half ago. And if anyone knows the answer to whether there's a new mechanism in place inside of the Beam for back pressure. So in the case of the Pony runtime, yes, there is. And I can talk more about the details about how that works. It's a little bit clever. The guy who wrote it took either 5 or 6 different implementations before coming up on one that doesn't deadlock in some kind of crazy way inside of the VM and inside of the runtime, or at least we think it doesn't deadlock. We're still not 100% sure. So here's the theoretical message delivery properties. We've already talked about causal delivery order. If you're specifying a protocol like Paxos or Raft or two-phase commit or those sorts of things, then you typically set out in the big bold print at the beginning of the description of the algorithm some certain properties of the messaging. Is there causal order or FIFO order, or what is the order of delivery messages? Is there message loss? With the exception of like dead sending to dead PIDs or something like that, there is no message loss. There is no message duplication allowed. Sort of accidentally by the runtime. If you're sending messages on a real network, of course, that maybe packets may be duplicated, but it doesn't happen inside of either runtime. And we already talked about message reordering, that there's a difference there. Do you interact with the outside world? And in both systems, the answer is yes. The Beam is much more mature in this respect, in having access to external program ports and ports. Internally implemented ports for representing file descriptors for sockets and file I/O and stuff like that, and then going off into wild fun land of having async I/O threads, thread I/O pools, and dirty schedulers and stuff like that. The Beam does have, or pardon me, the Pony runtime does have the notion of asynchronous I/O and timers that can generate events either caused by, like, say, socket I/O or timer expires, and then send messages into your application's Pony actors. Is Byzantine behavior allowed? No, in both cases. So we've reviewed all these things by category. The maybe off by one or two here, but there's like 9 sort of Pony woe differences that I had pointed out. And here they are listed in the top 4. I put it in a different color that you may or may not be able to see, but 3 things about message receiving, the message ordering, blocking versus non-blocking, and being aware of time. And then the scheduling thing, preemptive versus cooperative scheduling. So those are major points that if you wanted to compile or translate Beam to Pony or vice versa, these are fundamental things that you have to overcome. So it's not super easy, but if you want to attack this problem, come talk to me, because I think it'd be really fun. So just as an example for dealing with such a translation, like how do you do a synchronous call, like gen server style in Beam or Elixir? In a Pony, you can't do that, and the reason, one of the reasons, is that you can't block waiting. You can't block waiting for the reply because you're always handling messages in FIFO order from your mailbox. So it's like you're writing everything, all the messaging in bare, bang style or gen cast style messaging. But it is really possible to work around this stuff, and Pony is really fun, and it's really fast also most of the time. Creating applications that generate lots of these extra garbage collection messages, for example, is one way that you can slow your Pony things down. But for a lot of applications, you get similar efficiencies that you would find in comparable C++ code, for example, which is really nice. So I have a lot of references for the actor model, communicating sequential processes, and then links about Pony itself. Go to ponylang.io. Don't go to .com or .org or something like that at ponylang.io. And then blogs that from Adrian Coiler, who has summaries of the papers that talk about the Pony garbage collecting protocol and related stuff.
So I was wondering, you mentioned that Hewitt had this comment about garbage collecting idle processes. Is that
idle actors? Yes.
Idle actors, yes, actors. So in the case of either Pony or Erlang, how would you detect that you don't need? Did he mention something, or do you have something about that? Or?
So for a Pony actor, what ends up happening is that if no other actor has the tag, has the name of the idle actor, that means that no one has the address to send it a new message. And so that means that it will never receive a new message because nobody has a name for it. And so that's how it's marked as being idle and being eligible for garbage collection. There's no foreign reference to it via the name.
So what are the biggest barriers for sort of real-world adoption for Pony currently?
It's a small community. There is no corporate sponsor on the scale of Mozilla for Rust or Ericsson for the Beam. And so there's a handful of companies, like my company is on the order of 10 people, and we're the only company that I believe is really public about using this. The other companies that I'm aware of or heard rumors of, they're all in like financial tech, and they treat everything as secret sauce that they don't talk about at all. And so the fact that they're using Pony, they zip their lips, right? And so that's sort of the biggest adoption barrier. Rust with its related typing system, and Mozilla to help pay the developers working on the core part of Rust, and then its much larger community. I guess that would be the most significant thing. That and some programmers are skeptical of dealing with concurrency in an actor model or actor-ish kind of way, whether it's getting people to adopt Elixir or Erlang or not, like using p-threads and locking in semaphores, like that's good, right? Some people, that's how they've used to do things and continue.